I am delighted to introduce Professor Misha Gromov from the Institut des Hautes Études Scientifiques in Paris and also from New York University. So Gromov is without question one of the most inspiring and famous mathematicians living today. He is the winner of the Abel Prize, which is considered the Nobel Prize for mathematics, or one of them. He has a long list of awards, including Oswald Wellman Prize in Geometry, Wolf Prize, Boltzmann Prize, Kyoto Prize, Nemers Prize in Mathematics, Boyer Prize, and the Abel Prize, of course. So the list of topics that he made seminal contributions in Wikipedia is several pages long. In particular, he worked on Ricci flows and hyperbolic geometry and a number of very fundamental areas of mathematics that he contributed with seminal results. In particular, Riemann geometry, foundations, and hyperbolic geometry I would highlight. It is Gromov's Hausdorff measure is something used in computational biology group here at Brown as an important method for deep learning in genomics. So all over he made tremendous contributions, and we are very excited to hear Professor Gromov's von Neumann lecture today. Professor Gromov, you're next.
Thank you very much. I hope you hear me. Yeah? So, and it's my honor to speak on these lectures, because von Neumann was a great mathematician, and besides being a great mathematician, he one of the few of us who could relate mathematics to something else. And so I'll do such attempt in my lectures. And then before I show my slides, I want to say that this is not mathematics, it's just what I want to say. It is what precedes mathematics. It's attempt to imagine mathematical model of human mind or some aspects of human mind, and really kind of imagine what it is mathematically. And I don't think it's the final answer, but this kind of direction I think is interesting. And so let me now to show my slides, and let me see if I can do it. To share screen. Somehow I have to find the button, but somehow it disappeared. Here it is. Now you see my screen, yeah?
Yeah.
It's okay?
Yeah, we can.
Okay, good. So my point is that what happens, fundamental processes in your mind are mathematical, and they are invisible to you. You are not supposed to see them. And there is a good reason why you are not supposed to see them. They are blocked from your conscious mind, roughly for the same reason why mitochondria kind of separated, isolated from the rest of the cell, because its products may be poisonous for the rest of your mind. Something happened there. You are not supposed to see that, but there are instances when it comes to the surface. And I start with this example, which I think absolutely fantastic. This is not example. That's just a picture how you think your mathematics and your mind interacting. Yeah. But this reflection will be part of some moment I explain what reflection is happening there. And here is two formulas. And this is some phenomenon which happens in mathematics and was very particular. It was Ramanujan who read some book, and then what he produced. And so, and this transformation of symbols he received from the book, a symbol which he wrote, I claim, suspect, and know how to say it is a mathematical phenomenon. It cannot be explained by by words in any simple terms, right? It's just, and if you don't understand this, and refuse to understand it, then you are infinitely far from understanding how our mind works, in particular how it interacts with language and with mathematics. I emphasize 3 points of understanding. These are mathematical, language, and science, and this is twofold interaction. This is where I put these mirrors, and these are part of the interaction which characteristic of human beings is not presented in even in higher animals, right? Only in rudimentary form, of course, there is something you can speak about language and mathematics, but not this kind of mathematics. And usual, sometimes objection which can be made. You see this kind of, looking at them immediately see what understanding signifies. How much you want to understand these formulas, depending on qualification and knowledge. So personally, I reasonably well understand the first formula, but the second one, I can kind of understand it, but of course I don't understand the deep meaning of that, which are only available to people who knows it well. And this may be an objection, saying that this is a kind of isolated phenomenon, it's a rare phenomenon, whatever. But here I want to say that this is exactly wrong application of probability and statistics to this subject matter. That much of what I say justified by the fact, but statistical approach common in physics and borrowed to other sciences based on the following principle, and this mathematical principle, that average and typical essentially the same. And because average, what physicists and everybody else can compute, but this you cannot see. Yeah, experimentally you see kind of typical behavior, and this is kind of the law of large numbers, the simplest manifestation. And for the moment there is large body of mathematics analyzing it. It's called concentration phenomenon, which was emphasized, first brought to the life in this form by Paul Levy 100 years ago approximately, and then was popularized by various people and brought to the focus. And this remarkable phenomenon, which is non-applicable to biology or to psychology. So you cannot think you cannot exclude probability, but you have to change it radically and forget about this principle, or rather not to forget it, but know where to use it. Of course, it still has without it, very hard to use probability, but must be used in a very different way. And so this is exactly because it is exceptional phenomenon. It should be understood more than average phenomenon. Another example, if you look at the sky and see the stars, if you want to understand them, you have to first understand supernova. And these are very rare and very exceptional from our perspective, though of course they're very common in the universe because there are many stars. Because, as you know, no matter how rare they are, our life depends on them, not first of all, more than maybe than on such stars as our sun. Yeah. So, in the same way, and this basic process of understanding seen in this working of Ramanujan and his brain more than on the average. And at least I don't want to explain exactly what this. I can make the hypothesis why so, but it's another issue. But so this is what we have. What kind of and mathematics you expect? You don't expect to find explanation of your kind of mental process in understanding, and we rather kind of, but rather just to find a framework where we can talk about them mathematically and kind of objectively. And just the two inspiring example, of course, is this Galilean symmetry, which define Newtonian mechanics and most what we see mechanically in this world. And I emphasize non-commutative. So it must be understood. It's extremely difficult to grasp intuitively what is the structure of the group of SO3 or of rotation of the space. It's non-commutative group. And if you look at the best mind of the 20 years ago, like earlier, they have absolutely kind of on one hand, practically applicable, but no conceptual understanding what the group is, because existence of such a group, compact, non-commutative group, absolutely beyond our comprehension, no matter what you say. It's just if you take a physicist point of view, you just describe these properties, I would say, no, it's impossible. And this, by the way, true about much of the mathematics. Yeah, mathematics on any kind of significant level is science about impossible phenomena. On the other hand, another example is opposite, where we have something very simple. Mathematically, it's just exponential function, and this mathematical part was understood very much by Darwin. And it's amazingly, it was not properly grabbed by mathematicians at the time, but Darwin, on one hand, he didn't know multiplication table. He made mistakes in his computation. On one hand, on the other hand, he had mathematical intuition, and his intuition, and probably the same as Wallace, but I haven't read enough Wallace to say it. He understood that this is the right framework to describe evolution. Again, contrary to what some biologists say, it doesn't explain anything in evolution, but it tells you how to speak, no more than just the fact that law of motion obeys differential equation, but itself explains nothing, because you have to know the equation, you have to solve it. And even less so, this is natural selection plus explains evolution, but it allows you to talk about this in a constructive way, right? You know what are parameters, what to measure, what to look for, etc. And the point is, mathematically, you have exponential growth, you cut it off. And this is mathematics you can study and was pursued, of course, quite significantly. Now we turn to our mind, and so just what we have to reject is this terminology. So we have lots of self-gratifying words about how smart we are, and all these words, and I think they, exactly because there is a good reason why we say them, because so pleasant for us and self-flattering to say them, they must be absolutely irrelevant. I wouldn't say they're wrong, but certainly irrelevant to our understanding of our mental processes. This was confusion created a lot. There are many more of these words. I don't want to repeat them, but all these words about how creative, rational intelligence we are, and some of them just wrong, some of them just meaningless. And the dictionary, what we want to use, what I said, is universal, some universal entities where we can start doing mathematics. With creativity or intelligence, they have no mathematical counterparts. But all these words have many mathematical expressions, and we want to look at them. And so let's look at examples. Yeah, there is some, I said, there is this constant probability, and which in principle can take into account some correlation due to the inherent symmetry in biological system and in mental system, but symmetry very different from the one which we have in physics, of course, yeah. And but this is beyond the scope of my talk. But here is two examples, and this is the one example. You have the bug on the leaf, and so what you have probably observed as a child, just that if you look at the bug on the leaf, it spends much more time on the edges of this leaf, yeah, somewhere here, and it was even more so, but not proportionally much more than inside. Really, just even in absolute time, not to say divided by area. So why it happens, right? And you say, I want to say, it displays kind of one of these basic principles of how brain of this animal works, and our brain works very similar. I haven't have these pictures here, but if you look at how your eye would do this, if you look at this leaf, your eye will behave more or less in the same way. You spend more time. It's a particular point here, at point here, on the boundary, but less than inside. No, but your eye will be spending some time along this line also. And so, what is mathematically different? And there is one obvious things, and this is one of the universal you have to use, that amount of information you receive here is different. Here is a boundary. So here is one, here is another. So you have being present here, receive one bit of information. When you hear, you forget about this particular pattern, so there is no information. So empty space. It's just zero kind of information coming to you when you move. And here you can kind of being on the boundary. It's more interesting. I interpret it in this way because it's more informative and more interesting. Of course, information I use in informal way, right? It's a mixture. Of course, I'm saying the word bit, but of course, it's information relative to the system which observes it. So it's not information of a Shannon type. It's a questionable entity which is unclear if properly definable, but in concrete situation, you can observe it. So this is the one instance, right, of a mathematical pattern which is present in your mind. And so it is an understanding of edges of information. And so and it's kind of mathematically the whole mathematical theory you can imagine when you perceive world, perceive geometry in terms of so-called information you receive. This, of course, needs formalization. Another example, probably many of us familiar, is that how, by again, very formal process, ants as a community behaves in an intelligent way. So again, interesting feature mathematically here, that all these ants are, for this purpose, identical. So they behave in the same way, right? And so, and this defines this particular nice behavior, namely when there is a source of food, and some ant find the source of food, they come there, or several ants, and eventually they find shortest path to that, and everybody goes along the shortest path. And how they find the short path? And this is interestingly because it answers, the way they do it, answer to the famous kind of quotation by the Haldane. The Haldane was one of the smartest people ever working in biology, or in general, one of the smartest scientists of the last century. And what he says, he didn't like the idea that something was, his brain was, his mentality was governed by chemistry in his brain. He definitely resented this idea in what he says. But exactly chemical smell define behavior of ants, because what happens when they go to somewhere, they trace they leave some particular smell along their path, and so if the path is shortest, given an equal condition, there will be more ants going there, so intensity become maximal. So the shortest path has maximal intensity of smell, and therefore being preferred by following ants. So it's extremely simple algorithm, and again, conjecturally, something like that be happening in your brain. Now, I must say, I'm not so much concerned what's happening in the brain and how this mental process is being implemented by the brain. There is a big gap, right, between the two, and this is not my business to fill it in. But the question is, what is in between neuronal activity, which we kind of understand, and our mental behavior, which also we observe. But the point, just I am kind of underlying what I'm saying, there is intermediate stage, which is neither of the two, which is not expressible in the common language. It's not something like your dream or your subconscious, nothing like that. It's really very far from any conscious perception or any kind of perception. And it is like behavior of these ants, Right, so we are not interested exactly how they produce these pheromones, which you put whatever, but the fact they are there, and then there is very simple. Another example again, which I find especially nice, is that a baby animal pretty fast learn how to distinguish goose from hawk. If there is another goose flying over them, they don't pay any attention to that. But if it's hawk, they immediately run into cover. How do they learn that? And in artificial intelligence, there's a lot of talk about top down, down top, kind of logic. It's unclear how have to classify that. But the point is, it is the exercise maximally abstract reasoning. You see, it's not concrete, and then they don't generalize. It's neither. But so how they do that? It was actually, I think, it was Tinbergen and other people were involved in Tinbergen. He formulated the right conjecture. It was confirmed. And they don't have in their mind picture of a goose or hawk a priori. But what they are able to distinguish goose from hawk. So they know the shapes are different, right? So it's one thing. They don't know what these are. They know they may be similar or different. And again, it is a very abstract general principle. It's number one. Secondly, what we know, some event is frequent or rare. So they have different events, something flying over their heads. They see something. And they know some of these events similar and some different. Right? So we don't have to know what events are. What we only have to know some are similar, some different, and some repeat themselves. So they can see repetition, and then they can count. They don't count in numbers, but they know event frequent or rare. And then it's very easy strategy. First, they always run into cover. If something happens, something changes, this is another fundamental phenomenon of the life. Mostly nothing changes, right? Things changes are rare. Boundaries take smaller amount of time and space than interiors. This is true in our geometry, and it's true in our life. And there's a kind of famous story about Fermi, who was making bets during the Second World War, always winning. And his statement was, nothing's going to change. And so usually you win. But on the other hand, you know, if you always follow this strategy, eventually you lose horribly, right? So, but locally you win. And so the same about, so things eventually change, yeah. So it's very dangerous to think they will never change. They do change. It has to change, but most of the time they don't. And so they run always, because most of the time nothing flies over their heads. And then if something happening too often, and there is a probably built-in idea in their brain, what does it mean to sufficiently often to ignore this, then they don't run away, because hawks appear rarely, right? Because there are much fewer hawks than geese, because hawks have to eat geese, and so there are 100 geese at least for each hawk. So this is and this is actually how we function. Our brain works the same way. So again, the point that I want to make: you can use mathematics. You have a hope to use mathematics, because there are some universality in the processes which determine your mental states and mental behavior, whatever they mean. And so you turn to that. Now I did it only because I couldn't put my to put pictures in the right order. But this, by the way, nice pictures, and they, you see, they're kind of pleasant to look at for some reason. And it's another story why. So also mathematical, by the way, regardless of their shape. And then the last one is some discovery made by Douglas Spalding long time ago, and usually ascribed to different people unjustifiably. And this is a imprinting, that how baby chick knows who his or her mother is. And this is abstract thinking. Again, it's the first moving object. So again, this concept of the first and moving an object. So there are three concepts, very abstract, of the same type we had before. First moves object. Something changes its state, constant or not. And experimentally, you know, and it was much popularized by Lawrence, who makes these experiments, and you can use any object. And this, by the way, was known before Spalding. It was observed by people before Spalding, but he was the first to make experiments on the leathers. And he's not as commonly known as he deserves. He was contemporary of Darwin, and he was really a brilliant, absolutely brilliant mind, and he died young because he was poor, and usually, like most people of the time, died of tuberculosis. And I think he kind of deserves to be remembered by psychologists. Psychologists, by the way, when I spoke to some of them, they hate his name because it's not kind of science they like, yeah. And it's very mathematical, yeah, by the way, behavior of these animals. It's another, by the way, how it's happened, they go in one line, how they know Euclidean geometry. It's another point, because the laws of mathematics so simple. Now come the following quotation by, there are many quotations by Einstein, and my impression and actually this also applied to many quotations of Darwin. Most popular of these quotations are just fake. Yeah. For example, this one is for some reason I want to bring it up. It's this something to do. It was what I'm going to say, but certainly, obviously, it's not Einstein. So if you have very common thing ascribed to a great man like Einstein or Darwin, it will be again for interesting psychological reason why such sentences being ascribed to great people. But what is the difference, however, between knowledge and understanding? Because understanding, because we speak about understanding, comes in many flavors. And any of us are probably familiar with that you're at a lecture, yes, for example, if it will be mathematics, physics, bioinformatics, and if you really understand what happens, you're tired after 1 hour already. But if you listen to something like anthropology, you're not getting tired. You can listen 5 hours in a row. And the reason is that it's combinatorially different things which happens apparently in your brain. I don't think it was ever checked by maybe visible in MRI, because the amount of blood definitely different. You probably feel exactly how much energy your brain consumes depending on what you do. Because when you learn something, you create much more connection in your brain. It's a graph, kind of first approximation. It's a network, and if it is just it's just knowledge, you just have kind of a tree, and then in this tree if already you have ready places to put these things, you put it there. If there is no ready place, of course, you get hard work. But even a subject you know very well, like for me, it would be mathematics, is the hardest to listen because it requires maximal amount of transformation in your brain. And now, so what we learn and what we come out of that. And so the point is, so what you have, what comes to your brain is something like that, and nothing else. So you can forget, well, of course you cannot forget it, otherwise it's impossible to describe it. But temporarily we forget the subject matter of what we want to learn. It may be mathematics, language, or science. I will be emphasizing mostly mathematics and language, which is just before our eyes. And so you just have parallel signals going into you. So it's essential there's several parallel, but of course it's difficult. Sometimes we will pretending there's only one sequence of symbol going to your mind, to your brain, and that's all you have. So specificity of the world disappears, and you have to recover this. So the point is how to looking at that, recover the picture. For example, it may be something coming from your eye. Of course, it's not a one flow. It's several parallel signals going simultaneously. Languages better. Languages have very simple one-dimensional flow. The amount of your brain power involved is minimal, and this, by the way, specifically human. Especially when it comes to understanding formulas like that, yeah, you cannot claim, for all my respect for various animals, there is no animals who understand it, even among us. For example, the second formula is understood maybe by 100 mathematicians in the world who understand the second formula. The first formula understood by most mathematicians, and the second already. However, I'm saying it is definitely very specific. So why, and I'm saying this might be much simpler than understanding something else in our mental process, because, for example, this behavior, this kind of, this has longer history, right? Evolution of these basic reflexes was working probably at least 100 million years. And on a rather large population of animals, especially when it's coming to insects, yeah, it was really lots of insects. So it going on quintillions experiments that nature could make. However, if you look at us, at human, that by the most optimistic estimates, when we were separated from chimps, and it was about 5 million years ago, the number of tries evolution had was well below 1 trillion, right? Because population, for the most part, was just several thousands. And there was some bottleneck when it was just 1,000 roughly. It was never above 1 million. And so the number of children born, say, there is one, in this population, one child, each parent have one child every year. So the number of births and deaths was tremendously small. So, and however, with this very small number of tries, some very sophisticated programs, well, sophisticated as we perceive them, and claim they're not sophisticated, but they look sophisticated. programs were produced which allowed us to make this, say, understand language, understand mathematics or science, which is not characteristic of animals, and which even for human is requires a particular effort. It's not natural for us to understand mathematics on high level. It's counting 1, 2, 3 up to 5, okay, but that no more than that. Then you have to do something in your mind, but your mind has this universality to do that. So it must be very, very simple programs. So by random choice, you make 1 trillion tries, with trillion huge might look big, with tiny number compared to number of configurations and possible programs in very few symbols. And this is it makes you hopeful you can do it yourself and guess what it is. And so what I will be describing is a skeletal of what you can call understanding. Yeah. And from the skeletal, I'll give you only a rough idea of the creature. This is actually a skeleton of a whale, and certainly hardly you can see a whale, but and so what it is. So what are basic elements out of which this understanding is built? This is kind of in the first approximation of that. So what I want to describe at this level is the next would come from a physicist's analysis of a language. So there is, this famous manuscript, Voynich manuscript. It's a book. It's about 300 pages, written in unknown language, unknown topics, and nobody can say even if it's human language or it's a hoax, right? And physicists analyzed the statistical distribution of patterns and found out, well, it agrees with human languages. And so this is the first what the physicists do. They see repetitiveness of certain strings and their correlations, and well, there is some pattern. And we have to imagine the next level of that, which tells you more about the structure of the language. In particular, if you can guess if such sequence of symbols carries some meaning or it doesn't. So, but of course, meaning is again an interesting word, which was much discussed by linguists, and so we will be careful. So these words we have been using in 2 ways, and sometimes usually. By the way, I'm not certain when I started how long time I will have. I think I have 55 minutes, and I think I spoke already 40, right?
Can you hear me,
Yeah.
Dr. Gromov?
Yes, I hear you.
You have, if you could finish around 10:40.
10:40, yes, this is what I expected, yes.
Perfect.
Okay, thank you. And so out of which we make our network. So it will be network with extra structure. It will be hierarchical, multi-scale colored network, right? So it's network, then network of networks, and also there will be colors. So networks is binary relation, and colors are unary relations. And some of them come from within, like what we see on this animal. There is no network. We see this atom of thinking. This will be there, but some of these nodes of this network coming from outside, like we shall see, like words. Yeah, this will be one of the units. So, and this is a basic conjecture which can be objected. We take discrete model, and apparently there is a good reason for languages. Language is discretization of our thinking, and all we know about our conscious thinking is by language. Everything else is just you cannot say so it's there or not there. We forget about that. So it is discrete. So it will be something discrete. However, many of these units may be a little bit vague, like it happens with genes. What is a gene? It's a little bit vague notion. Which particular segment of, even when we say it's a segment of DNA, it's already kind of different from a gene of classical genetics, yeah, which corresponds to some protein or to some visible feature, right? Even there, which segment you regard as gene is vague, yeah, and it's okay. So it will be discrete structure, but with certain allowance to be stochastic or ambiguous in some way. So these are basic units. There are units, and then there are relations between these units. And there are 2 types, very different kind of relations, fundamentally different, though both like not quite binary, but at this stage, think about them as binary. One of them, similarity between certain units, and we don't know a priori what kind of similarity, right? But just something similarity. In a second, let's say what makes them different. And co-functionality. And the fundamental difference is that similarity doesn't depend where they appear in our perception. They may be very fine, having nothing in common, but still have words in different books. It's still regarded as the same word or something. For us, it's just something similar. But things which are co-functional must be in part of a bigger unit where we work together. They cannot be separated much. So there is the concept of two fundamental different concepts. Of course, there is another delicate situation here. You see, I will be speaking about using mathematics, but I'll be very careful in that way, that it's not any kind of, I use much of the standard mathematical language, on the other hand, none of any specific mathematical idea or theory, which is sometimes you can see people take their beloved part of mathematics and try to use it for modeling, say, our mind. And I think it's a priori wrong idea because, well, we don't know what it is. And most likely it's unknown mathematics to us. It's particularly concerning probability, I would indicate what are obvious modifications we have to make to probability will become not so elegant as we have, and to apply it to languages. And you know that Chomsky was always objected to using probability in languages. On the other hand, today the way to make artificial system of translation depends on statistics. It works very well. But the point is what kind of statistics and how it's being used, right? So you might be careful about that. So, and then just one particular point is that one structure we must be very careful with is order, because the way I understand it, if you say A greater than B, and then B greater than C, then A greater than C, this cannot be explained, formulated in a certain mathematical language, right? For the reason, because you cannot order two entities, define their order, unless they already be ordered, either by being written on the line, on the blackboard or paper, which has internal geometric structure, or in time. And the time is your internal psychological time. So you assume that your time and time of your to whom you speak, they're the same, and we know it's tricky because we are not aware of true time which happens in our psychology. Therefore, order and again, experience of most of us, so that order comes later. We always have mistakes. Who is sign? You see, if you say A, B, the order sign between them, how you know how it's directed? Because you have to say beforehand that B goes after A. Unless you know that, you cannot say what sign of order means, right? So this is a very essential point, and I think it's not properly appreciated, which actually underlies the more subtle logic in mathematics, like Gödel theorem, crucially depends on that, on this argument. You bring in this artificial order. You cannot formulate, or rather, you cannot make the main step in the Gödel argument unless you have that. And so, which, in my view, make it not that rigorous as people usually say, because it depends on, it's more or less of the nature, the same as when you say some people knows left or right action of the group on the space. You know left from right. You know your left hand and your right hand, but we know that you only can say it because there is break of symmetry, violation of symmetry in the weak interaction. And if you don't know that, you cannot tell left from right, and so your language depends on this physical phenomenon which was discovered recently. And so it's a little bit absurd to take it seriously. Yeah, and indeed it is different in your. So there are different levels of mathematical sophistication inside of this network, and the order is much higher level than just similarity or co-functionality, which is symmetric when you have a non-symmetric entities. So again, so you take mathematics very, very carefully. You have to be more critical to logic than logicians are on one hand. On the other hand, this mathematics must be not logical mathematics, it must be really mathematical phenomena which must enter the game. So my point is here that there is in common, what joined together our mentality, our brain, our mind, brain, I don't know what brain is, just your mind, what you can do, you can prove this theorem, it's a remarkable thing, and mathematics itself. And they both about impossibilities. What happens in mathematics for any rational mind who yet understand mathematics but doesn't know it, it would be impossible. Any non-trivial theorem in mathematics is something about impossible. You can prove from general principle, it's just probability of this is close to zero. And that's exactly what mathematics is interesting. And the same about our brain. If you could say to somebody educated entirely in physics that there is such thing as living entities or thinking entities, say it's absurd. It's exactly all physics based on hidden, unspoken assumption, that's impossible, right? And he's very, I dislike when you bring this up. And so it is about impossibilities. So with mathematics, you must be careful. You don't use mathematics, you only use mathematical way of thinking. But unfortunately, we cannot do it without using what we have. So, and so our learning process, so not our conceptual understanding is inseparable of conceptual learning, because this network is a dynamic entity, and we don't know what it is. And here is another basic mathematical idea we borrow from mathematics, that we don't know how to say what particularly this is. What is this network we want to describe? And it may be very, very much from person to person, from situation to situation. But the class of this, universe of this, must be, in my view, describable. So, and for example, it's very difficult to say about some physical constant what exactly value of this constant is. But you know, it's a member of a community we understand. It's just a number, and we know what numbers are, assuming we take mathematics the way it is. Yeah, and here is an example from mathematics. Just I want to. Because this is a not kind of, again, not properly known to mathematicians away from this field. So he sees here, this are algebraic curves, the radius formulas. And then people, mathematicians, worked and wanted to give what is the curve? What is this algebraic curve? And this was kind of foundational algebraic geometry. And there was a book written by André Weil, where he summarized kind of principle of mathematics developed up to 1950. And so in 1956 or maybe 1960, he wrote his book Foundational Algebraic Geometry. And then, maybe 2 years later, came the Grothendieck definition, what's algebraic curve. And Grothendieck definition of André Weil was very natural definition. It was a set with certain properties, the definition. And I remember when I was learning it, it was so nice. Just you felt almost yourself you could make the definition. But then came definition of Grothendieck, and everybody, of course, at least for beginners like myself, was shocking, rather absurd definition, because he was not defining the curve, but defining some category of a fine scheme, But then time came, and we know what everything natural, nice definition by André Weil was absolutely inappropriate. It was just historically motivated. But Grothendieck, now everybody uses only Grothendieck's point. And it's one of the essential ideas. You don't define so much this curve. You define community of objects, a very large community. And this community of schemes or some category of scheme, and only there you can locate what are these algebraic curves, because you cannot define them in isolation. And therefore, it's much easier. And to say what a particular curve, what this equation, it's come much later stage. And you can think, aha, this is very abstract, it's very difficult. But this is, again, it's not, I don't think it's correct. Say, thinking of category theory of mathematics is most elementary thinking. Children think in those terms. Physicists, classical, if you translate what Boltzmann, how he was describing ensembles of particles, exactly was thinking in these terms, and was criticized by von Rieger, by mathematicians, up to a certain point, because exactly they didn't have in their position these kind of things. As Grothendieck emphasized, zero, not very difficult thing. It takes century for people to come to the idea of zero. And this is the same about category theory. It's the same level of abstraction as zero. It's on the bottom of our mind, but it doesn't come to the open. And I think there are other things in the bottom of our mind, some logical thing happening there, which don't come to the open, and they define what I want to describe. And now, so what is understanding? As I said, understanding is particularly language. And language, of course, very nice because you have huge amount of language now on the internet, and you see how much you can understand it and what this understanding means and what language is. And just this instance of that, so this definition of algebraic curve is a big success in mathematics. Mathematicians were able to define what is algebraic curve. But certainly mathematicians fail to give definition of a language. And there are some mathematicians try to say language is a set of strings, or language probability measure on the set of strings. And this, of course, is linguists would laugh at that justifiably. Yeah? And so what is the language? And so I say, well, this is a kind of symbolic representation of reality or some other kind of words. So this is a good example, yeah. So you understand this sentence, but what the hell means you understand it? Right? This is exactly in what way we understand language. And this is kind of quite bona fide sentence, a bona fide idea, but it's very tricky what you understand with another language. And I haven't brought enough examples, but I'll bring in a second more of them, yeah. And language is actually, transformation to language is very much how we understand even visual patterns. And visual patterns, it's another matter how we understand visual patterns. And there are two fundamentally different types of what we perceive and analyze visually. So I have only 3 minutes, yeah. And in our vision is very much determined by a life system, which is completely different from one which is pure nature. Here is an example. Yeah, so you look at that. So from certain formal point of view, both pictures are very much the same. It's the same colors and the same shape. But they are fundamentally, the question is, are they fundamentally different? Or is just because we know the face is the face, right? So can you tell the difference? And my guess from individual, from these two, it's not enough. But if you have 10 like that, Martian is not a Martian, but kind of what you see on the moon and the Mars is like that, and or not necessarily faces, but faces in animals. And then you can see that there is fundamental difference between them. And so your understanding applies only to this thing like faces, but doesn't apply to this kind of landscape when there's a random landscape. So the way you can understand something depends on what you understand. And something will be beyond your understanding, and some mathematical method like Fourier analysis, wavelets, whatever, can tell you much more than your mind. So now I wanted another idea we can borrow from mathematics, only say how mathematics may be used. That there is certain commutativity. This is a kind of fundamental concepts in mathematics, and particularly in operator theory, which describe physical systems, is commutativity. And then the point is that in most or many rules of grammar can be learned independently one from another. The order doesn't matter. And this is another point. The order is kind of a tricky point. And therefore our time and also it's partly due to the fact that your brain works in parallel. And in parallel means it has different structure for its description. You see, sometimes say, oh, your brain is parallel, give you extra power. We know computationally it's no. Sequential computation is more difficult to make parallel than the other way around, right? So parallel in a way more primitive on one hand, and this is true about many things in your mind. It's more primitive than you do in computers. But on the other hand, it gives you different possibilities. When you have a two-dimensional picture of your time, you can make pictures there, which you cannot do so easily on one-dimensional. And that is the point, yeah. So you bring this artificial structure. It's there in your hardware. It's parallelism. And over this, you can introduce something else. Yeah. Well, so my time is running out, and so I show you just some example of sentences just to amuse you. Yeah. This, by the way, true quotation by Einstein. Yeah. And this interesting point, and some people say that means that there is some great design in the nature, but it's because one of the things why the world is comprehensible, and this is crucial for our analysis, what you do, because mostly it's empty space. And so nothing happens except in the boundaries. So there are some interesting feature of the signals which we receive. Again, very simple. Yeah, for example, this one. So this is a famous story. And again, I just want to emphasize a mathematical point where apparently there is no mathematics. Right, so you read it, I hope, and so down to Ansel, we solve. Right, so again, this is this similarity, the same man appear in different contexts, and this gives you a link between different parts. So this similarity may link together. This again, the similarity linking different events is characteristic both of what happened in biology and in human minds. So now it is something about meaning, but I wanted to show you for the last some simple examples. Yeah, it's again, yeah, it's how this relate to this. So all I describe here, there are some mathematics. One algorithm, maybe I want to say, which you are well familiar with, and which is fundamental in this, is B clustering. Of course, in bioinformatics, you systematically use B clustering, and it works remarkably. And this also works in, I believe it's one of the fundamental mechanisms which works in what we call understanding. So this, but I want to show you example indicating how tricky is the idea of understanding. Yeah, here it is. Yeah. Yeah, here is a sentence again, and you kind of understand it. But this, I wonder, if you slightly change the words, if any present computer would pass this kind of Turing test. If we spoke about goat and then we speak to the cow or something like that, and so we understand the sentence in a very tricky way. Just look at this, and you see how it's different from understanding the subject what is written in the rest. So imagine we had that, and then we ask this question of your computer and see if it's able to answer you. And in principle, I bet you will not, because the self-reflection of the language in mathematics is one of the ingredients. Because see, you know, language, even more than mathematics itself, has this kind of self-similarity structure. It has any small part of the language can incorporate the whole language. And in mathematics, it's essentially a feature of the Gödel theorem, which is Gödel theorem, or rather proof theorem, says that mathematics is fractal. The tiny piece of mathematics can reflect the whole mathematics and can be repeated infinitely many times. And this is a structural property of Gödel theorem. And this is what we remember in our model. Our model must have this property, which is very, very delicate property, which is very hard to formalize. And this is one of the difficulties which we hear here. Yeah, that's another famous joke. Yeah, and again, we understand that it's interesting. Again, the basis for our understanding of the sentences. And so, the problem is it is really kind of almost purely mathematical, which is I don't know how to solve it, but I think I can formulate it. That if you have this class of graph, I can describe what kind of graph they are, which would reflect some reality. And the point is that if you find that, if you make the structure, it cannot be wrong. And this probably with Bclustering algorithm. If your Bclustering works successfully, it couldn't be by accident. Probability of accident is virtually zero. So, but I wanted to show some examples just for. So I'm here describing what properties we know this mathematical object must have. You can, on the basis of your experiment or what you know, there are some number of properties. It's typical of humanity. You have to don't go too deeply into that. Even very superficial property like I described, if they're satisfied by this mathematical model, it will be fantastic. You can construct such model because a priori such model is impossible. But in mathematics, many structures are impossible. So you look for mathematical structure, which model your mind. And if you can formulate this property, you think it shouldn't exist. But because we believe mind exists, and this should exist. In mathematics, it's okay. In mathematics, often things which you think don't exist do exist, or almost always so. And just to entertain you, I just give example of certain sentences when, see, as usual, yeah, it's impossible.
Yep.
So one thing we have to be careful about logic. Yeah, this is an example. Yeah, Socrates' motto. My time is over, right?
Yes. You have like 30 seconds left or so.
30 seconds, yeah. But I wanted to show you some sentence just to make you. See, I didn't clean enough this talk. I was. Well, probably of course, I didn't hope to come to the end, but in the end, I was showing something amusing. I lost it. I was just explaining. No, I couldn't find what I wanted to say. But yes, I want to give some extra examples when you see sentences of different kind and how you understand and completely, the understanding of one and other have nothing in common. And so just I want to emphasize a point that your understanding is not some unique entity. It's a member of huge community of mathematical objects, which we want to define. And these entities interact because your understanding is dynamic and exists in many stages and had this self-similarity similar to the one we observe, say, in mathematics by Gödel's theorem. And, well, of course, its description takes a long time, yeah, and it's conjectural anyway, because as I said, it's conjectural structure, which potentially may imitate a model, what we call understanding. And this understanding, returning to my first page, we do know it is there. We either understand or don't understand it. And so there is difference between two states of the mind, understanding and non-understanding. And you want to understand the structure of this. So what is in your brain happens when you see and start understanding either of these two. Okay, this and of course, all what was, of course, in the brain of Ramanujan, but not on the neuronal level, but on the level of deeper logic, which generates such entities as these formulas. Okay, so I'm open to questions.
Thank you so much. We have time for maybe one or two quick questions. One longer question or two quick ones. Okay, I'll ask, I don't know if this is quick, but so Dr. Groma, does your mathematical model of the mind have anything to say about philosophical concepts like consciousness or free will?
Okay, you see, at the very beginning, I said it, yeah. It's just I say these words, I have nothing against them, but they're not interesting. They just, you can speak about them forever. They exactly brings us in a completely different mode. I don't want to say anything for or against it, but they're not a priori formalizable. The model which I have in mind is to understand and to improve the working of artificial intelligence, because we have these neural networks and they work fantastically well. But we don't know, we have no mathematical model what happens on the intermediate stages of this computation. And I think you can tremendously improve that if you know what you do, right? You don't do it in blind way, and it's kind of blind search by iteration, but make it more organized. And what is this consciousness or free will? I don't know what it is. You can say, I actually personally, I don't know what people say about it. People say these words. For myself, I don't know what my free will or my consciousness. You have to be convinced, you have to learn that there is this concept and convince yourself it's there. I don't know, I don't have it. If you don't brought from the childhood, you say you have free will, you have free will, you don't have free will. You have it, of course. You behave in some way, you don't have this idea. I think it's a cultural idea. These are both cultural ideas, and okay, like being good or being kind of free or whatever. These are okay, but I don't know. I just personally, internally, I don't know what means I myself, whatever. There's deep philosophical meaning. I think philosophers with a certain mentality have this very strongly, and then pushes the idea on us. And I resent it in a way because I don't want to be trained or manipulated by philosophers. Mathematics is, these formulas is reality. You read this formula, it is a reality. And, you know, as said Democritus, or at least, of course, he never said it, that there are only empty space, moving atoms, everything, the matter of opinion. And so this is a matter of opinion. And, sure. and it's somebody's opinion is of no interest to us. We only want to know the reality, which we can put your finger on mathematically or scientifically. They're very two different ways, but both, which, well, productive. And the other are not free will, yeah. Yes.
That's fair. Thank you so much. Let's have another round of applause for